then the next speaker is Professor Jayashree Kalpathy-Cramer. She's the Chief of the Artificial Medical Intelligence in the Department of Ophthalmology at the University of Colorado. Previously, she was an Associate Professor of Radiology at Harvard Medical School, where she was actively involved in data science activities with a focus on medical imaging. Her research spans the spectrum from novel algorithm development to clinical deployment. Her lab has been actively involved in research in topics related to bias and fairness in AI. Dr. Kalpathy-Cramer has authored over 200 peer-reviewed publications and has written over a dozen book chapters. So it gives me great pleasure to introduce Dr. Kalpathy-Cramer for her presentation.
Thank you so much for having me here today. I am hopefully going to share my screen shortly and share some of the work that we have been doing in the area of medical imaging AI.
That looks good. It's on screen now.
Excellent, thank you. Some disclosures. As you've heard today and will continue to hear today, we've seen a lot of AI and machine learning being used throughout the workflow of a patient's journey, a cancer patient's journey, from the time the patient comes in and might have some symptoms to deciding exactly what protocol is appropriate for that patient. There's a lot of work in AI in the use of optimization of the image acquisition. So going from raw data in an MRI, for instance, in case-based data to the final image, or from sinograms and CT to the image. A lot of that happens today using machine learning and AI. In terms of diagnosis, that's where we've seen probably a bulk of the work in medical imaging AI is in that area. We've heard a little bit about some of the molecular markers and other things as well in terms of optimizing treatment response and a variety of steps in this process, almost all of which use AI these days. Historically, cancer imaging has been somewhat qualitative. If you look at radiology reports, you'll see often sort of descriptions that are really hard to translate into a mathematical equation. So it might say things like moderate heterogeneity or highly speculated. And it's really one person's moderate heterogeneity, maybe somebody else's severe heterogeneity, for instance. So these things have been much more qualitative. As somebody once said, a radiology report is an extreme form of data compression, in that you take images that are many, many bytes of data and you take them and make them one word or a few bytes of text. So the goal now with a lot of what we do in machine learning is to try to get some of these to really get the images and the data in the images to be much more quantitative. Here's some example from mammography. Again, if you're looking at what a mass is, there are many things that might distinguish a mass, or especially one of concern, and things like shape and margins and density are all what a mammographer might look at. So the attributes, again, that people look at are the shape. So things like what the shape is it the borders irregular, or what the margins look like, is it speculated? All of these things have been traditionally used by radiologists to try to assess the likelihood of concern, of reasons for concern. So as we sort of go along the journey in the use of machine learning in imaging, one thing that we have seen is trying to quantify some of these things. So how do we come up with numbers that capture the previously described attributes of a tumor? So people look at things like sphericity, which is essentially how close to a sphere the tumor might be, versus objects on the left had like more high sphericity versus the ones on the left, which are essentially have a lot more, where the borders might be a lot more uneven, might have low sphericity. Texture is something else that has been again noted in radiology reports for a long time in terms of having values. So the notion of heterogeneity, again, this notion of texture has been around for a very long time. And what we have seen more recently is the interest in trying to, again, capture these mathematical definitions of what a tumor might look like on an image in radiology, for instance. This concept is called radiomics. And the idea, again, is that there is a lot more information than we have been capturing in terms of the data that we get out of an MRI or a CT. So can we somehow quantitatively capture these differences between what might be benign versus malignant nodules? And this term in this context has exploded in utilization, as you can see here. And it's been used for many, many things, and it's continuing to grow. So the idea with the radiomics workflow is essentially you have an MRI, for instance, of a brain tumor. You might segment the boundary of the tumor. You might extract some features. You might do some normalization. And then you essentially capture features that might indicate the shape, the size, the texture, a variety of things like heterogeneity. And all of these features can be extracted. And then often you do some feature selection potentially, and then do machine learning like random forest or whatever your favorite machine learning tool is. Of course, there are challenges throughout this workflow. So for instance, changes in how you acquire the image and how you reconstruct the image can change the appearance of it, and the features might not be robust to these sort of differences. How you pre-process the data in terms of how you, for instance, bin the histograms in terms of before you do your feature extraction can be different. If you just have slight variations in the tumor boundary, for instance, again, that can lead to completely a substantially different set of features, for instance. The mathematics of the feature extractions can be different across sites, and then obviously the model building. So although radiomics has had a lot of success, there are definitely many challenges. More recently, we have seen deep learning become extremely popular in imaging. A lot of the things that we used to do in terms of classification and so on that we did with radiomics, very often now people are using deep learning to do. And some of the applications of deep learning here are segmentation. So segmentation is the task of outlining the boundary of a region of interest, and very often that is a tumor, for instance. Response assessment, so is a tumor getting bigger or smaller in response to therapy? Radiogenomics, image registration for longitudinal assessment, survival prediction, drug delivery. So a variety of things people and approaches have been applied for radiological imaging in cancer. So an example of that is glioma. So for instance, if you have a brain tumor, your patient might come in with a headache or some symptoms that might suggest that maybe they should get some MR imaging. There's a fairly standard set of images that are required. This could be pre and post contrast, T1 images, T2, flare, diffusion, perfusion, and so on. Often a biopsy is done to assess whether it's what kind of tumor it might be. For instance, a treatment regimen is selected, and then response assessment is needed to see if the patient is responding to therapy or perhaps a change is necessary. So a lot of the work that our lab has been doing over the last many years now is how can automated tools improve patient care in terms of delineation and detection of tumor boundaries, treatment response assessment, non-invasive prediction of molecular markers, for instance. Segmentation, again, is a very common task that deep learning excels at for many things in oncology. So segmenting tumors in radiological images, in pathology, and a variety of different images is another fairly common and tractable task. Besides segmenting tumors, deep learning and other approaches have been used to segment all kinds of organs. So in radiation oncology, for instance, you might want to segment organs at risk, in addition to the tumor itself. One reason why we think it's important that we have these sort of automated methods is that there's a lot of variability in the manual contouring. So this is the data on the right is from an actual clinical trial where 2 readers were reading each case and measuring the volume of the tumors. And as you can see in the top left, there's substantial difference even at time point 3 between the 2 readings. In the graph on the bottom left, you can see at the 4th time point, suddenly they diverged in whether the tumor grew or was stable, and so on. So again, this is not a new discovery. We've seen this reported in the literature as well. We've had many studies where we've had multiple raters do segmentation. And if you actually look at their contours, you can see substantial differences. So the goal is that if we can automate this process, perhaps it'll be at least more consistent. So our fairly standard deep learning algorithm, we used it a few years ago now to create tools for doing the outlining of the flare and enhancing tumors, and showed that we had pretty good agreement between what the algorithm said and what multiple humans said. And in fact, the algorithm agreed with sort of the consensus of the humans more than they necessarily agreed with each other. Now that we've had the ability to find the tumor volume at one time point, the question now is the patient responding to therapy? For brain tumors, a response assessment criteria has been established for a while now. And essentially the goal there is this sort of algorithm, so to speak, a step-by-step process in which the tumor's burden is assessed. And although it sounds easy, there can be a lot of challenges. You first have to find the slice with the largest tumor area. This is done visually, and it can be quite different in terms of even which slice is chosen by the different experts to measure. We were looking over a radiologist as they were doing this assessment, and were trying to ask them, how do you select which slice is it that you want to use? And their description was, we pick the slice that really captures the essence of the tumor. And we were like, how do you now sort of write that into a mathematical formula? I want a slice that captures the essence of the tumor. Then we find the largest measurable diameter. We had to exclude necrosis and blood. We had to find the largest sort of measurable perpendicular diameter. And depending on the shape of the tumors, and especially in something like GBM, which has fairly complex shape, there can be quite a bit of variability in how these sort of assessments are done. You multiply the diameters, and then you add this up for the 5 lesions. And there can be quite a bit of variability in each of these steps, which leads to a compounding effect. In terms of the assessment of this particular way of measuring tumor burden, if we ask two people who are in the same institution who sort of work together a lot, and therefore we expect them to have much more agreement with each other, we find that even there's only sort of moderate agreement between the raters. So our goal here was, now that we have a pretty good algorithm to automatically segment the brain tumor, can we now automatically also get these bidirectional measurements, because that's what is typically used in practice. Although there has been a lot of interest, at least among the computer scientists, in trying to get the field to move to more volumetric assessment, still what happens in clinically very often still tends to be uni or bidirectional measurements. So what we again show that we are able to assess the change, so delta between time points, with very good agreement between the manual and the automatic measures. We can also show that our measure of automatic RANO measurement is actually better representative of the true tumor volume compared to, for instance, the human-derived measures. A related project that we were looking at for brain tumors is the establishment, just looking at imaging. Can you say if this tumor is IDH mutant or not? There had been a lot of interest in this kind of approach from imaging. What sort of characteristics of the tumor can you assess? And so IDH seems like is one of the more straightforward ways, because even humans can look at it and sort of have a reasonable guess as to whether it's wild type or mutant. Not perfect by any means, but at least enough that we think that might be a signal there. So we had trained a deep learning network to essentially find a virtual biopsy, as our student called it. So whether you have the wild type or the mutant version of the tumors, can you get pretty good results? And we were able to show that we get pretty good results. Once we have the ability to now segment, the question is, can we segment everything? You acquire so much data all the time. These deep learning networks, CNNs, are really, really good at segmenting tasks. So can we just segment every organ? So can we automatically extract quantitative information about everything that is required? You already have the scan. Why not use it for other things as well? So segmenting all sorts of organs is something that people have been looking at. And there's a lot of interest now in this notion of opportunistic screening. So if you're already getting a CT scan, can you, or MR, can you do things like body composition? So can you do muscle, and can you do fat, and can you do other things? And there's, again, reasons to believe that these can be useful for in the course of a cancer patient's progress. So we've seen things like sarcopenia and cachexia being associated with outcomes. So if you are in a position to automatically extract all of these attributes, such as muscle, fat, and so on, maybe you're in a position to then sort of stratify your patients in terms of good and bad outcomes. Switching gears a bit, I was going to talk a little bit about the work we're doing in cervical cancer screening. So this is work with the National Cancer Institute with a large team of people doing different parts of it. We've been working with them on the AI development for the images. So it's a leading cause of cancer morbidity and mortality worldwide. And the HPV virus is one of the strongest risk factors for essentially transitioning to cancer. And in many low and middle income countries, the typical standard of care is to do visual inspection after the application of acetic acid. Although this is really not recommended and has been shown to be not as reliable as we would like it to be, this is still something that people continue to do in some parts of the world. So the question is, instead of doing this sort of in a human way that is potentially subject to a lot of variation, can we train an algorithm to do the same sort of tasks? So can you now analyze the images of the cervix after the application of acetic acid, look for things like whitening, and can you then do it in the context of a large screening and triage kind of approach? Again, we see that the burden of the disease is concentrated in a lot of Africa and more low and middle income countries, parts of Asia as well. And so the goal, again, is to try to come up with a low-cost approach that can be deployed worldwide, but with a focus in places where cost is a big concern. So this is a sort of moonshot initiative, and it's the PAVE program. And the goal is to have first the self-sampling for HPV testing and typing. So at the end of that, you essentially have the highest risk, which is 16, and then you have sort of stratified risk based on just the HPV genotyping. You then, for the women who are HPV positive, you might then go on to using this device, sort of a handheld device, you get images after the application of acetic acid. You stratify the risk based on the appearance of the cervix after acetic acid based on a computerized algorithm, and then you combine it with a treatment regimen as well. So this was something that had been studied quite a bit by colleagues, again, at NIH, and they showed pretty early on, a few years ago, that the ability to train a deep learning algorithm to do that is actually is quite good, and the performance was quite good. One of the challenges, of course, with a lot of these deep learning algorithms that we'll touch upon in a lot more detail is that they tend to work well in the populations that they were trained with. So the external validity can be more challenging. If you train and test sort of in the same data set, even in a set-aside sample within the same data set, the performance can be substantially higher than what it might be in an external population. So we heard the previous speaker talk about this notion of generalization. And so that continues to be something that is really critical as we think about deploying these algorithms, especially in a sort of worldwide context. So I'm sure everyone here is quite familiar with ChatGPT and large language models and AutoML and a variety of other things as well. So with all of these tools that are coming on board, it's getting really easy for us to start to create AI algorithms. We have students in our lab, high school students even, who, if you say, here's some large data set, we have some positive cases, we have some negative cases, you have pre-trained networks like from ImageNet, can you go train a classifier? It really is becoming fairly straightforward to do so. As long as you have annotations, data, you can toss it all in and out comes a algorithm. You can ask ChatGPT to write your abstract for you. It does it phenomenally well. You can ask it to write your grant. It does that well as well. Despite all of that, there are obviously many issues. And this follow-up publication from the same group at NIH highlighted some of the challenges in terms of essentially going from an algorithm that is the first step in terms of something you're happy to publish to something that is really generalizable and deployable in a robust manner externally. And these are some of the concerns that they had raised in this publication, including reproducibility, external validity, device portability, and so on. And so I'll spend the next few minutes touching upon many of these aspects and explored some solutions that we've explored, but many of these are still open areas of research. So maybe at the end, I'd love to hear from the audience if you've encountered these and what sort of approaches you may have taken to mitigate some of that. So here's a list of some of the concerns that we have faced when we go from sort of a, again, transitioning from something that was one publication to something that is really worth deploying when you're really going to be affecting a lot of patients' lives. So generalizability, models tend to be brittle and do not generalize across scanners, populations, disease presentations, and so on. The second one surprised us. Model predictions are not repeatable. We have seen actually very little of this in the literature. So if you have retest data set of the same person imaged at roughly the same time, what you really hope is that the algorithm's output is the same. And we found that, shockingly, that was not the case. Another area is this concept of a gray zone. So many diseases lie on a spectrum, but we often tend to treat the ratings as binary or maybe ordinal. And how do we sort of think about equivocal cases or sort of an intermediate zone? Often because of the nature of how we train the models and the cost function we use, the models can be poorly calibrated. We can have silent failures where the models may fail without indication. They can be confidently wrong. Explainability is something that has been raised as a big issue with deep learning models because, again, of the black box nature of these. Overfitting is something that we worry a lot about. A lot of literature is extremely over-optimistic and has results that are often not reproducible. We saw this a lot during COVID times. There were many publications during COVID, most of which had results that were really extremely optimistic and not reproducible. And some studies looked at maybe 300 to 400 of the publications and basically said not one of them is really ready for prime time. So again, as deep learning and other methods of machine learning get more popular and really easy to implement, this is something we need to worry about a bit, more than a bit. Models can be biased, and this can be in different ways. Again, since you're learning from historical patterns, you can learn those patterns, encode and propagate these biases. So we have to be quite sort of careful about making sure that we assess the models for bias. So the first problem is the notion of this brittleness. This was from a couple of years ago, but deep learning models often do not generalize well, and very few studies have actually looked at external validation. The data heterogeneity can lead to poor model performance on external data sets. There was an interesting work that looked at how the FDA, which is the US organization that looks at sort of certifying or getting models stamped for approval, how many of them actually used external data sets, how many of them did prospective studies. This is a sort of living document, living website where as new models come on board, they keep it updated. But you can see that not a lot of them have external data sets or prospective validation. What does that mean for us? If you think about taking pictures of a cervix with different cameras, for instance, you can see right away that the images can look quite different from a sort of visual perspective. And these can be things that are obvious and clearly seen by a human, or it can be much more subtle. Photographers from the old film days know the differences between Fuji and other film like rolls, and you can tell almost looking at the image which camera type it came from. The same sort of thing happens here with different devices and different camera types, and potentially with different people taking it from different geographies and so on. So one of the questions that we always wonder about is the deep learning model somehow normalizing for these differences? We always had been told that the early layers of deep learning networks do things like normalization and sort of more basic features. But what we continue to see very often is that if you look at, for instance, a t-SNE or UMAP of the features of the trained network, sort of the last but one layer features, and separate them into clusters, what the clustering is not the disease that we really hoped it would be, but rather the device. So what we always had hoped is that when you see different clusters, it's because there's sort of different clusters in the features as for different disease states. But what we really see is different camera types, different scanners cluster very separately. So often the networks seem to learn the device first and then the pathology second, which means that if you have now a third or fourth device, it may not necessarily sort of work well on this external data set. Here we have the same person imaged on 3 systems, and we really had hoped that the same person, same image would look a lot more entangled than we see here. So this is quite a bit of an issue. Here's data from the cervical cancer screening question, the automated visual examination. So this was a network that was trained with data from one device. On the diagonals, you can see when you train and test on the same device, the performance is excellent. But when you train on one device and test on another device, the performance is barely better than random. That is very much of a concern, because now you have to retrain your algorithm for every device, for instance. If you did happen to have data from both devices and train both, you get excellent performance on both. But this notion of portability, meaning that if you have an algorithm that was trained on one camera system, one scanner, and you can just use it on a different device, is not fully borne out quite yet. There are a lot of different approaches that are being considered to do that, but that's a work that is still in progress. So things that people have looked at is increasing the data diversity, really focusing on multi-institutional databases. And certainly the work that Dr. Pryor and other of his team have done in creating systems like the Cancer Imaging Archive, where we get data from multiple institutions, are one way in which we can sort of help the field along. Another thing that I think we really need is a good way of detecting out of distribution. So if you have a trained network and now you have a new data element from a new person, a new scanner, we need to know if the algorithm, if that new data element is close enough to the training data that the algorithm is more likely to work or not. If it comes from a completely different distribution, perhaps we need to be extra cautious before applying that algorithm to that new data set. We also need better methods for improving the generalization. Federated learning is sort of a different way of getting access to multi-institutional data sets. So instead of having sort of central repositories, perhaps the data can stay behind institutional firewalls, but we can still learn a model that is has seen data from multiple institutions. Because of the lot of concerns about patient privacy and regulations in terms of data sharing, this might be a tractable way forward as well. Some of the work that we've been looking at is, can you predict, given a distribution, as to whether, do you have a good measure of distribution differences that translate to prediction of the performance in the new data set? So if you had data from scanner 1 and scanner 2, and you see a tremendous drop in performance, can you, without having ground truth, sort of tell you how well the algorithm is going to work in this new data set? So there's been a number of different approaches that we've been looking at, but conformal predictions is one way that we can look at for looking at distribution shifts. So in terms of an evaluation plan, I think it's really important that we curate multi-institutional and multi-scanner data sets. We might, as we are developing algorithms, we might want to think about ways in which out of distribution inputs can occur. And that can be things like different scanner types, different quality, even things like we are expecting a frontal image and you get a lateral image, or and are we putting guardrails around that? How do we make sure that the data going into the network is what we expect it to be? The second question that I wanted to touch upon is this notion of repeatability. So here is our two images of the same person. To our eye, to the human eye, they look very, very similar. But on the left, the model predicted is as a normal case, whereas on the right, the model said it was pre-cancer. We see, so if you plotted the probability of the output of the network as a test-retest, you can see we really want it to be along the diagonal, but we see these off-diagonal elements that are pretty substantial. Again, same sort of things. We've looked at it for multiple data sets. So we looked at it for cervical cancer, for ophthalmology, for X-rays, and so on. And in all of those cases, we find that the models are surprisingly not repeatable, especially depending on how you train them. So if they were trained as a binary or 2-3 class classifier with fairly sort of sharp boundaries, this problem is even becomes worse. So one way to think about why that might be is this example, this sort of toy example here. So we have a set of data points where we have the classes and controls, and you can see that the algorithm has trained a decision boundary between these two set of points. Suppose you had a new point, which is the star. It is pretty close to the decision boundary. So when you train the algorithm one time, for instance, it is in the red part of the decision boundary. Now we retrain the algorithm with, and because many of these things are stochastic, we get a slightly different decision boundary. And now maybe the star is essentially on the cusp between the two classes. And yet a third algorithm trained again on the same data set, because it's slightly different starting conditions, or however small differences in the stochastic nature of the training process, and now it's firmly in the blue. So we can see how the probability of this data point in being one class or the other might flip-flop, and that, which is obviously terrible. You cannot have an algorithm that you can deploy in practice where small variations in how the image looks will cause the algorithm's output to go from class 1 to class 0. So one way in which people have approached that is this notion of ensembles. And so instead of having one model, you have 20 models in this case. So you get this nice smooth boundary. And so instead of saying that the probability of the star is either 0 or 1, maybe you say it's 0.4 or 0.6. And at least that way, you know it's close to the decision boundary, and you need to be a little more careful about how you interpret the results. So in our case here, we looked at cervical cancer as well as knee osteoarthritis, and both for sort of a binary as well as multi-class problem, we can show that if we do something, this notion of ensembling, but through this Bayesian Monte Carlo approach, we show that we get much improved repeatability. The Monte Carlo approach is essentially you have a neural network, you randomly drop certain connections during the training process, and so you get multiple different networks that are slightly different from each other, but you also do the same thing potentially at inference. So you now have 20 networks, and you take the average probability of the output of that. And what we see is that it really does sort of modulate this flip-flopping and gets it much closer to it being much, much more repeatable. So our strongly recommend that when we are thinking about deploying these algorithms, we have a data set that where you can really truly look at repeatability and reproducibility. So if it is ethical, acquiring test data sets is great. Often, if you have ionizing radiation or other reasons, you might not be able to do that. But even if you cannot, perhaps you can do things like, I mean, a lot of this happens as part of the training. You often have all of these augmentations, but really sort of explore how to mitigate against that would be helpful. The third problem that I wanted to touch upon was that real world is often a continuous spectrum. In the top row, we actually have data from two different use cases, one in ophthalmology, one in radiology, where the same set of images was given to 8 or 5 experts, and they were asked to bin those images into 3 or 4 classes, so sort of a mild, moderate, severe grading. And what you see right away is that some people have a lot more red and some people have a lot more green. And this tends to be fairly consistent. So it's probably not a surprise to many of you, but clinicians are not perfectly concordant with each other. They have their own set of biases. Some people are overcolors, some people are undercolors. And we often see this manifest itself as in a situation where like if you plot things on an ROC curve, for instance, you might see that people lie on different parts of the ROC curve. In terms of the same problem manifesting itself, we've seen this in public data sets where if you have rater 1 versus rater 2, you can see they lie on one side or the other of the diagonal. So in addition to raters being sort of along a spectrum, the disease itself can be along a spectrum. And if you don't respect that nature of the disease and try to say everything is binary, perhaps you run into this issue of flip-flopping and grave errors. So for instance, in the cervical cancer situation, we have where we have sort of normal and pre-cancer, we can see a lot of grave errors in the off-diagonal elements by introducing a sort of intermediate gray zone class, for instance. We can see that we have a little more fewer grave errors, and so more things that lie on the diagonal. Excuse me, sorry about that. So a different solution that we've also considered is this notion of, instead of having binary outputs, having a continuous output variable as a function of severity of disease. So in terms of an evaluation plan, I think it's helpful to have multiple raters. We see this quite commonly requested when we are publishing deep learning manuscripts that are using humans as the ground truth. It'd be really good to also have data sets that are along the disease spectrum, so not just the most extreme cases, and then looking at more nuanced cases and seeing how well the model works. Problem number 4 that we want to touch upon is this notion of silent failures. Very often, for instance, when we're looking at a DICE score of a tumor, for instance, what we see is that it has a long tail. People typically report the median or mean value, but really rarely talk about this long tail where the algorithm completely failed. It might be a small minority of cases, but the problem is that you don't know without ground truth which of those cases that might be that failed. So trying to come up with ways of establishing the uncertainty when the model is more doubtful for it saying, I'm not going to say anything here, might be better than it's being confidently wrong, which is often something that we see. So again, Monte Carlo type approaches or other approaches allow you to identify the cases potentially where human oversight may be necessary, or at least you should be very careful about using the output of the algorithm. They can also improve calibration. calibration is often not shared in publications, at least in earlier stages of the radiology deep learning publications. Calibration curves are not shared that often. It's starting to, people are starting to use them more often, and really trying to figure out how well calibrated the models are is really important. This is a fairly recent publication, actually, from just earlier this year, saying there's no such thing as a validated prediction model. And there are many reasons for that. Patient populations might vary. So basically, all of the kinds of covariate shifts or label shifts or things like that can cause the association between the model's output and the input to change over time as well. So I think the sort of take-home message is we really need to understand model calibration. We need to continuously monitor the model performance, get a good sense of what are the characteristics of failures. Are there sort of attributes that might help us understand what are the failure cases? The next problem I want to touch upon is this notion of overfitting. So we see a lot of publications where we see, again, overly optimistic results. And we did a look through some of the publications in the literature. We randomly sampled 50 of them and looked through the kinds of mistakes that people often do. A lot of it was for the more radiomics type approaches, but the same sort of thing happens with deep learning as well. So for instance, if you are not very careful about how you split your training data from the test data, and where you do that, there's a leakage that can occur. And often what people tend to do is do feature extraction first, for instance, before doing the splitting. And that if you do that, then again, that's one way in which leakage happens. So here were some of the things that we found in terms of what we call sort of mistakes. So in terms of, are you using do you not have an external data set? Do you are you doing when and where and how are you doing your hyperparameter selection? Are you using your test data in any way for that? Are you doing any kind of, are you using your test data to inform any part of the model building, model evaluation, except the sort of the very final part? And what we show is that if we, many of these mistakes sort of compound, and essentially using a random feature set. So what we did is took real data from TCIA, 2 data sets, and we had essentially random features generated with true outcomes, and showed that we were able to associate these random features with the true outcomes by doing all these mistakes and going from essentially a random AUC to perfect AUC, essentially, by doing all of these things. And so we then looked to the literature and found that many of these mistakes happen more frequently than we'd like to admit. And again, we showed that you can essentially go from really good performance to random performance as you get rid of your mistakes. So really important to have statistical rigor throughout the process. So a lot of things to think about. Above all, have a statistician on your team who is really working with you and understanding ways in which data leakage and other things can happen. Are you doing multiple testing? Is there an external data set, and so on? And this is one of my favorite XKCD comics. We've seen this, I'm sure, but basically you can keep testing till you find an answer that you like. And that's what it often seems like happens in the literature, unfortunately. The next topic I want to touch upon is this notion of black boxes. So deep learning models are often considered to be black boxes in the sense that you have an input, something magical happens inside, and you have an output. There are many methods people have used, post hoc methods such as GradCams or saliency map approaches. And this is fairly common in the literature in radiology. One reason in which this has been helpful is that these things have, for instance, highlighted things like markers. So what it turned out was the deep learning network was not really looking at the lungs when it was trying to recognize pneumonia, but it was actually looking to see for a marker in the shoulder that might indicate whether the patient was taken in a prone position or supine position, which might, portable X-ray versus not portable X-ray, which might say how sick the patient was. So there's this notion of shortcuts, and the concern often is that we are learning shortcuts and not sort of true associations. So people have tried to use these kind of approaches to see what the model is looking at, if it's truly looking at the area where it should be. On the other hand, there's been pretty strong reaction from some people in the community saying that if you're going to use these black box models, really don't try to use these post hoc explanations. And this is the bottom one is a more recent publication that again highlighted what they say the false hope of explainable AI approaches. So one way to potentially think about that is, can you develop inherently more explainable model? So instead of just saying positive or negative on a sort of patient level, can you say, here's an area of concern? Anytime we work with clinicians, not just for cancer, but for anything, they would much rather sort of have a bounding box saying, here's where the model thinks the issue is, as opposed to having to scroll through hundreds of images, potentially in a CT scan or an MRI to find where there might be something. And it can be quite frustrating when the model says, yes, there's a issue here, but not saying where, and they cannot find it. So they may end up spending more time trying to find it than otherwise. Segmentations can be good too. Again, if you have a model that says, here's an area and here's where it is, that might be useful. So then so we have a plan that we suggested might be useful to evaluate how good these saliency or other approaches are. So the first one is, do they actually highlight the area of interest? One concern that has been raised by other authors, and we've reproduced some of that, is that each time you train a slightly different model, the saliency map looks different. The model output might be the same, but the area I highlighted might be quite different. Or you essentially have a trained model and you randomly change some features, and what you might notice is that the model is not changing. What we really hope is that the saliency map is really associated with the weights of the model and not just things like contrast in the image. So here some things to think about. So the next thing I want to touch upon is this notion of bias. There's a lot of concern across many people. We see it all the time in the news as well, about the potential for deep learning and other AI models to encode and propagate bias. So this was some work that colleagues put together recently, which is a fairly comprehensive listing and sort of glossary of the different kinds of biases and where they can creep in. So things like data collection, model development, model evaluation, and so on. So, and many of them can be in multiple places as well.
So just to say, there's 5 minutes to go.
Okay. Yeah, almost wrapping up. So then we've seen this again. So we've seen that in healthcare decision making. If you use things like expenses as a proxy for health, you can essentially have a biased model. And there's some really good work done there. We've also seen where things like skin pigmentation can lead people behind. So especially with talking about things like melanoma and so on, we can see that many of these models in dermatology really perform in substantially lower performance in darker skin patients. We saw that during COVID when things like your pulse ox was quite not as reliable, again, if in darker skin patients. So making sure that the models work for all of the populations in which they are intended to be used is really key here. This was shocking, surprising work to many of us in radiology. Given a chest X-ray, you can train a model to tell what the self-reported race is. And this is, again, no one has quite figured out what is going on here, but many people have reproduced this work, and basically the model seems to be able to be trained to say, based on a large data set, what self-reported race might look like. And that seems to persist even with all kinds of slight alterations. So a lower resolution, high frequency bandpass, or different kind of alterations, and the model is still quite good at doing so. Same sort of thing, looking at your eyes, and especially even the vasculature, you can sort of train the models to pick up things like hidden attributes such as race and sex and so on. One of the concerns is that most of the data used to train models, at least in the US, has come from very small part of the population. Only 3 states essentially were represented, with most of the country not contributing at all. And it's even worse when you think of it from a global perspective. So we also want to think about this notion of fairness. So how do we make sure that the models are fair, especially when there's a sort of interplay between attributes that we are trying to measure, like breast density and breast size and self-reported race and so on. So really thinking of achieving fairness can be quite challenging. There are many different definitions of fairness, and that's even probably the first challenge, is to figure out what is the definition of fairness that you might want to use in this situation. So some approaches to doing that, again, getting large data sets with more diversity of data is useful. Really making sure that you evaluate how well it works in subpopulations, understand when it's not working, and so on. We've seen a lot of publications of sort of superhuman capabilities, so doing things that humans cannot. And this is looking at fundus photos and predicting cardiovascular risk or sex or smoking, a variety of other things, or looking at a mammogram who's going to get breast cancer 5 years from now, for instance. Humans are not very good at these tasks, and the algorithms seem to be quite good at it. So given that these algorithms can do things that humans cannot check, and given that we know that they have a potential for being biased, I think what we have to be really aware of is the need for constant vigilance. So making sure we continue to test model performance in all of the populations of interest, and really, really carefully looking at concerns about hidden bias as well. So sort of summarizing, here are the things that we think about before model deployment. So what is the reproducibility or portability of the model? Is it repeatable? Do you have sort of guardrails in terms of where you can and will apply it? Is it calibrated? Does it make grave errors? Is it confidently wrong? Or is it can you use sort of the pseudo probabilities to at least warn you that it's not very sure? Is it explainable? Is it biased? It's fair? Sort of how do you monitor it in real life? So with that, I will thank you for your attention.
Thanks very much for that great talk and a really interesting description of the problems with what you might naively think is an easy task for a computer to look at something and say that's a cancer or that's not a cancer. It's amazing the complexity of the whole thing. One of the questions I have about this is what's the concern if you're running a particular scan through a screen for, say, breast cancer, and it will miss other things that it doesn't know about that your radiographer would find and say, well, I can
absolutely see. It is a huge risk. Most of what we have done so far, or what we've seen thus far, has been very narrow. It'll tell you exactly that. You could have a huge bleed, but if you're not looking for it, it won't detect it. And that is very much a challenge. And that's why many radiologists think that they're not, despite proclamations otherwise, they're not out of business anytime soon, because they do a lot more than one little thing at a time. There are efforts to create more comprehensive tools that will look at more conditions, but they, again, tend to be limited to that. So, yeah.
Now, I was wondering, was there a participant who had their hand up? Attendees, there is one with their hand up. It's are we able to turn Tyrav on so that they can speak?
Hi there, can you hear me?
Yes, we can. Thank you.
Hi, Dr. Kalpathy-Cramer. Thanks for the great talk. My name is Dr. Bagrati. I'm from South Africa. And I just wanted to ask a question just regarding the cervical cancer and the imaging parts of your presentation. And maybe it's something I'm not fully understanding, but I just wanted to find out, how does AI truly help advance the field of cervical cancer in the future, or is this more of a hypothetical training model for imaging? And then the reason that I ask this is because in the diagnosis of cervical CA, we're going to be doing regular pap smear follow-ups for both precancerous or cancerous lesions, and even if there isn't cancer, or there is, we can detect it quite easily on histopathology, diagnosing carcinoma in situ 1, 2, or 3, and even immunohistochemical staining, P16 or Ki67. So do you see any true application of this in the future, in the long term?
So it's a good question, and I think it really depends on which part of the world you are and what is happening and how cost effective it is. So I think in terms of best practices right now, I think HPV typing is really important. So if you have HPV 16 or these other types that are particularly worrisome, then I think, as you said, there are other ways in which you can assess stratify risk. But what still happens in many parts of the world is the visual assessment of the acetic acid. So essentially, the goal is to help places where that might be still what is happening. And I think just the visual inspection of the cervix using an AI algorithm does help sort of stratify risk beyond what we have seen. So the study, which is happening right now, is actually going to screen 100,000 women over the next 18 months across the globe. And they self-sampled HPV typing followed by this visual inspection. And so the goal is to be extremely cost effective. And so we'll know better in a couple of years if this is actually helpful or not.
Okay, perfect. Thank you so much.
Well, thanks very much. I don't think we have any more questions in the Q&A. So we'll move on. Thanks very much, Jayashree, for your great talk, and we'll move on to the next speaker.